Molecules having multiple chiral centers. Now, we're in a chapter on isomers and stereochemistry, and this is the third lesson in. Now, we started off by looking at isomers in general and constitutional versus stereoisomers, and we introduced the term chiral center. And then in the second lesson, we went through and showed how we could assign absolute configurations to these chiral centers, and we saw that they were either going to be designated R or S. And now we want to take a little bit closer look at molecules that have multiple chiral centers and some of the unique things to them and some of the vocab that comes up specifically in this context. Now, if this is your first time visiting the channel, my name is Chad. Welcome to Chad's Prep, where our goal is simply to make science both understandable and maybe even enjoyable. Now, this is my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a lesson. So for molecules that have multiple chiral centers, first thing I want to deal with is just how many possible stereoisomers are there going to be here. So if you look, if I put, let's say, a chlorine right here, so all of a sudden this is a carbon that's bonded to 4 different groups. It's got a chlorine, a hydrogen not drawn in, and then the carbon of a methyl, and this carbon of the bigger chain here, and that's 4 different groups. And so this could exist in 2 different forms, and I could represent those 2 forms if I make the chlorine attached with a wedged bond versus having the chlorine attached with a dashed bond. So that would be one way. So but the idea is that when you've got a chiral center, it exists in 2 forms, R and S, as we learned in the last lesson. And so in this case, there'd be 2 different stereoisomers. But what if I add another chiral center? So this carbon's bonded to 4 different groups, a bromine, a hydrogen, and then these 2 carbons are definitely not equivalent. The right-hand side of the molecule and the left-hand side that has a chlorine are totally different. So 4 different groups, another chiral center, and then this chiral center can now exist in 2 different forms, R and S. And so all of a sudden, the total number of stereoisomers now goes up to 4 because you have 2 different versions. The way the molecule could look at this chiral center, 2 different that you could have it look here, and they're 4 different overall. So notice it could be RR, SS, RS, SR. 4 different versions. And this is kind of the same principle behind like flipping a coin. When you flip a coin, there's 2 possible outcomes. You can flip a heads or you can flip a tails. If you flip a coin twice in a row, you can get 4 different possible outcomes: heads, heads, tails, tails, heads, tails, tails, heads. So if you flip it 3 times, it'd be 8 possible outcomes, 4 times, 16 possible outcomes. And it turns out the more you flip it, the more possible outcomes. And it works on a principle of 2 to the n power, where n is the number of flips. Well, in this case, we're not flipping a coin, but we're just adding chiral centers to the molecule. And n here is going to represent the number of chiral centers. And the more chiral centers you have, the more different stereoisomers that could possibly exist for a given structure. And so in this case, with 2 chiral centers, we figured out it's going to be 4 possible stereoisomers. With 3 chiral centers, let's say we put like a fluorine right here. Now all of a sudden we got another chiral center. Now it'd be 8 possible, stereoisomers. And it's always 2 times 2 times 2 over and over and over again, with a couple exceptions though, as we'll see. And so the way we phrase this is that 2 to the n, where n is the number of chiral centers, equals the maximum possible number of stereoisomers. Now, it's interesting that we say the maximum possible number, and we'll find out that you're not always going to hit that maximum. It turns out in certain cases, when you're dealing with molecules that are fairly symmetrical, you might actually end up with less than that maximum. So it wouldn't apply to this molecule here, but we will see some examples here before we get to the end of this lesson. Now, I don't actually want to deal with this lovely molecule. The one I want to deal with is this guy right here that has 2 chiral centers. So, and with 2 chiral centers and no chance for symmetry, we would expect to have the maximum 4 possible stereoisomers, and I want to draw all 4 here. So in this case, the chlorine could be on a wedge and the bromine on a wedge, or they could both be on dashes, or a wedge and a dash each. Okay, and there's our 4 different stereoisomers. that are possible. Now, the next thing we got to deal with are some relationships here. Now, we've already learned the terms enantiomers and diastereomers. But just to review, enantiomers are stereoisomers that are mirror images. Diastereomers are stereoisomers that are not mirror images. And to rewind back a little further, stereoisomers are isomers that have the same bond connectivity, but a different three-dimensional arrangement of the atoms. So all of these have exactly the same bond connectivity, but definitely the three-dimensional arrangement of the atoms is different. Now, in this case, none of these are lined up in such a way that you can see if they're mirror images. But a couple of them definitely are. So if we took this molecule right here and rotated it around 180 degrees, it would look like this. And I'll put it in blue here. So 180 degrees would put the bromine over here, and now it would be a wedge. And again, 180 degrees out of the plane of the board would put the chlorine over here, and now it would be sticking out of the board instead of in. And now I can see that, oh yeah, they are mirror images. That is totally the mirror reflection right across the mirror plane here. So it's hard to see that they're mirror images right here, but they are. And again, stereoisomers that are mirror images are enantiomers. And I'm going to kind of put a E here to represent that they're enantiomers. And one thing you note with chiral centers, if you got one chiral center, you're chiral. And if you have the R version, then the enantiomer is going to be the S version. Well, when you've got many chiral centers, you have to invert all of them. And so if we assign R and S here real quick, so here chlorine's number 1, this carbon's number 2, this carbon's number 3, 1, 2, 3, number 4 hydrogen's in the back. So a right-handed turn is going to correspond to R. Notice how quickly I did that. You want to, maybe not quite that quick, but you want to get very quick at assigning R and S. It will be key to finishing this next exam involving isomers and stereochemistry. Same thing here, bromine's number 1, this carbon's number 2, this carbon's number 3, 1, 2, 3. That's a left-handed turn and it's S because again, the hydrogen, that's priority number 4, is in the back just like it's supposed to be. Now, if you notice here, the chlorine's on the wedge, the hydrogen on the dash, but in the next molecule over, the chlorine's on the dash, the hydrogen's on the wedge. And when we learned that when we have two groups trade places, it inverts it. So if this one was R, then this one here is going to be S. And if this one's S, again, bromine's on a wedge, hydrogen on a dash, now bromine's on the dash, hydrogen on the wedge. If the original here is S, then this one is inverted and is going to be R. And we've just demonstrated a valuable point. So we, again, know this is the mirror image of this compound. We just couldn't see it the way it was. However, a new way to recognize it, if you invert every chiral center in a chiral molecule, you'll get the enantiomer. And so here, I had two groups trade places at both chiral centers. That's going to be the enantiomer. Cool, so let's look at this. Once we've assigned one of the compounds, the rest are pretty easy because I can see if any chiral center is in the same or opposite configuration to the ones I've already assigned. So in this case, the chlorine's on a wedge, still on a wedge down here, exact same configuration, that's going to be R. But here, the bromine's on the wedge, hydrogen on the dash, here, bromine on the dash, hydrogen on the wedge. So instead of S, this one's going to be R. And then finally down here, again, I can compare this one to either this one or this one or this one, but here I can see that both of these are inverted. The chlorine's the wedge, the chlorine's the dash. The bromine's the dash, the bromine's the wedge. So these must both be S instead of R. And once again, we can see that when you have multiple chiral centers, if you invert all of them, you get a relationship that is enantiomers. Now, when you use that word enantiomers, it's always a comparison between two molecules. And in fact, that's true if you use the words stereoisomers, enantiomers, or diastereomers. Any of those three words, you're comparing two molecules. So if I asked you if my left hand is the enantiomer of my right hand, you'd say yes. Great. If I said, is my left hand an enantiomer, and I stopped. And you say, okay, Chad, finish the question. Is my left hand the enantiomer of my right butt cheek? No, it is not. It is the enantiomer of my right hand. So you've got to always compare something. You can't just say, is something an enantiomer? Now, I could say, is my left hand chiral? And that's a valid question. Chiral is a description for one compound. It just means that this compound, if I did compare it to its mirror image, would not be the same thing. So cool. So now we've learned very quickly with multiple chiral centers, we can actually recognize whether or not they're enantiomers if we actually assign R and S, which will be key in a little bit. Now, these are drawn in such a way that it's not too bad to see that they're inverted even without assigning R and S, but this will become handy later on. Now, on the other hand, what if I were to do a different comparison here? So let's say I was going to compare these two. Well, in this case, they've got one chiral center in the same configuration, one chiral center in an opposite configuration. So this means they're not the same molecule, they're not identical. So they're still stereoisomers, but they're also then not going to be mirror images. And if you're a stereoisomer that is not a mirror image, then you are, and you know what, I should probably do this in a different color. let's just keep this scheme going. So that means these guys are going to be D for diastereomers. And so this will be a common way we recognize diastereomers as well. If you have many chiral centers, if at least one of them is in the same configuration, but at least one of them is in the opposite configuration, then they're not mirror images. So they can't be enantiomers, which means they have to be diastereomers by default. So cool. So that's the case here if I compare these two. It's also the case here if I compare these two. So one of the chiral centers is in the same configuration, one is in the opposite configuration. Those are diastereomers. Same thing if I compare either these two, so one different, one the same, or these two as well. Again, one different, one the same. Cool, and so that's a common way we get to recognizing diastereomers. If you have many chiral centers and at least one is in the same configuration and at least one is in the opposite configuration, those are diastereomers. But don't forget, diastereomers, the technical definition was non-superimposable or non-identical, non-mirror images. And we also saw in the first lesson in this chapter that cis and trans isomers were also considered diastereomers. So don't forget, this is going to be a common way we often recognize diastereomers from here on out, but don't forget that cis and trans isomers are also diastereomers. Cool. So far so good. But this is going to get just a little more complicated here with the introduction of what we call meso compounds. All right, so if we're going to alter that just a little bit here, this original structure we had, and I'm going to take that chlorine and make it a bromine instead. And what this is going to do is it's going to make it that symmetry could be possible here, depending on the three-dimensionality of these two bromines, whether they're both wedges, both dashes, or if one's a wedge and one's a dash. So, and that's going to be important because we're going to learn a new way to recognize whether or not you have an achiral molecule. So let's say we take a look at cyclohexane for a minute. And my question for you might be, is it chiral or achiral? Well, one of the things we learned is to recognize when I've got chiral molecules is to look for chiral centers. Well, this guy's got no chiral centers. And that's true. Well, one other thing we could do, though, is just look at the definition and say, well, would he be the same or different than his mirror image? Well, if we draw his mirror image, so reflected right across a plane of symmetry here. So I can see that he is totally identical to his mirror image. There is no difference. Okay, definitely could identify him as achiral. Well, it turns out somebody figured out one additional way. And they said, if you can find what's called an internal mirror plane, so instead of taking and reflecting, the entire structure across a mirror plane, they said if you can find an internal mirror plane, and they called these sigma planes, in a molecule. And that's not the only one where, again, the right-hand side is the perfect reflection of the left-hand side within the molecule. And that's not the only one. I've got one going through this bond, one going through this bond, one going through these atoms. Cyclohexane's got a ton of them. But if you have at least one, you're automatically going to be achiral. It turns out if you have an internal mirror plane, then you're going to be able to not help but be identical to your overall mirror image. So now we've got a new test for finding achiral compounds. Any compound with this internal mirror plane, this sigma plane, is achiral. It's not the definition of achiral, but it's a new way to recognize achiral compounds. And this is going to be important in a second. That's why in dealing with symmetry here in a minute, we might end up with some achiral compounds. Now, we said early on that the easiest way to recognize a chiral compound, and I should say a chiral compound, is look for chiral centers. But there are exceptions, and those exceptions are called meso compounds. Meso compounds are achiral compounds, even though they have chiral centers. So here, cyclohexane is achiral, but it's not a meso compound. He's achiral, and we can see he's the same as his mirror image, or we can find this internal mirror plane. Either one of those would indicate that he's achiral, but he doesn't have any chiral centers, so we could not say he's a meso compound. So two parts of the definition of meso compound. He's achiral and has chiral centers, or achiral even though he has chiral centers, the way I like to say it. All right, so let's look at the different stereoisomers of this guy and see the relevance of this internal mirror plane. So here's our 4 possible stereoisomers, or so we think. In a second, we'll see that that actually is not the case. When we've got a plane of symmetry possible, like we do in this molecule, and we've got a perfect plane of symmetry if we drew it right here, or this one right here, but we don't have that same plane of symmetry here because one's a wedge and one's a dash. The 3-dimensionality means there's no plane of symmetry down the middle between them. But that's going to have important ramifications here. So if we assign R and S kind of like we've done before here, 1, 2, 3, this guy's R. So 1, 2, 3, this guy's S. 1, 2, 3, it looks like an R, but it's really S because the hydrogen's a wedge. The number 4 priority is a wedge coming out. So and same thing here, this one's going to be R, and I can just match them up. This one's R as well, but this one, instead of being S, is also R. This one's S, and this one's the opposite, so it's also S. And now we've assigned all our R's and S's. And if we go and define some relationships here like we've done, so these two are enantiomers. So I can see that I've got 2 chiral centers and they're both inverted, and that's going to get me an enantiomer. Okay, life is good. The problem is if you try to relate these two, you're going to come to a wrong determination because it looks, you want to say, well, Chad, you inverted both chiral centers. They should be enantiomers. Well, the key is if you have a compound with multiple chiral centers, and I should say if you have a compound that is chiral with multiple chiral centers, and you invert all of them, you get the enantiomer. But the problem is this compound's not chiral. With that internal mirror plane right there, it is an example of an achiral compound, just like we saw with cyclohexane. So it's a quick way to recognize if I can find that internal mirror plane, this automatically is achiral. And that's going to have an important ramification here. So being achiral, it doesn't have an enantiomer. So I can't call these enantiomers because he doesn't have one. So for an achiral compound, I mean, this is his mirror image. Don't get me wrong. These are mirror images, totally mirror images. But an achiral compound is not the enantiomer of its mirror image. It's identical to its mirror image. These are actually the same compound. If you flipped this one over, it would look exactly like this. And now the bromines would both be wedges. And yeah, you could say these are mirror images of each other, but they're not just mirror images, they're the same thing. And so as a result here, we didn't actually draw anything new by drawing this one right here. We drew this one over again. And that's why we're not going to hit the maximum possible number of stereoisomers. With 2 chiral centers, and we definitely have 2 chiral centers here, so both got 4 different groups. It turns out they have the same 4 different groups, but each has 4 different groups. And so with 2 chiral centers, we expect to get a maximum of 4 stereoisomers. We only get 3 in this case. And so when symmetry is possible and when one of your stereoisomers is a meso compound, you're not going to hit that maximum. And so it turns out this guy is the meso compound here. And again, there's 2 parts to being meso. He's achiral, and I can see that with that sigma plane again. So, and also has chiral centers. If he didn't have chiral centers, he'd just be achiral, but not meso. But because he's achiral and has chiral centers, or even though he has chiral centers, that's what makes him meso. Now, we introduced this idea of finding that mirror plane because it's often convenient for recognizing these meso compounds. But a lot of students, because it's the first time we ever brought up that internal mirror plane was for recognizing meso compounds, they think that any molecule that has the internal mirror plane here is meso. Not true. Any molecule that has the internal mirror plane, again, is simply achiral. You then have to also look for chiral centers for it to be further classified as meso. So note that all meso compounds are achiral by definition, but not all achiral compounds are meso compounds. So keep that in mind. Okay, so let's take advantage of one other thing here. So let's say I draw this a little funny. And I'll draw it like so. And all of a sudden here, I've rotated some of the carbon-carbon bonds in here, and I've represented this thing in a way that it makes it difficult to see if there's an internal mirror plane or not. You might have to rotate some carbon-carbon bonds around to figure that out. And so here's the deal. So at the beginning of this chapter, we briefly alluded to optical activity. We said that chiral compounds rotate plane polarized light. They're optically active. Achiral compounds don't. They're optically inactive. So keeping that in mind, what I'm going to tell you now is that chiral centers rotate light. That's what's actually rotating the light. So chiral centers rotate light, period. So does this chiral center rotate light? Yes. Does this chiral center rotate light? Yes. Does this molecule rotate light? Yes, because overall it's a chiral molecule. Now, in this case, with the Meso compound, it's a little bit crazy because does this chiral center rotate light? Yes, it does. Does this chiral center rotate light? Yes, it does. Does this molecule rotate light? No, it doesn't. So this chiral center rotates light, this one rotates light, the molecule doesn't rotate light. Well, the key again is realizing that you've got the same 4 different groups attached to this chiral center as this one. This one's got a bromine, a hydrogen, this methyl, and this half of the molecule. This guy's got a bromine, a hydrogen, this methyl, and then this half of the molecule. It's the same 4 different groups. But one of them's R and one of them's S. One of them's going to rotate the light one direction. One's going to rotate light exactly the opposite direction, so that on average, every photon of light passing through the solution will have encountered an equal number of these lovely chiral centers and overall won't be rotated. So that's kind of the deal. Meso compounds, even though they have chiral centers, don't rotate light. So I just want to keep that in mind because this is going to be a key to also finding another way to recognize a Meso compound, because here I look at this molecule, I'm like, well, it has chiral centers, and I know it's one of the stereoisomers of this, so there's a chance it could have an internal mirror plane if the 3-dimensionality is right. I just can't tell in this conformation if it is one of those. Well, in this case, the first thing I had to realize is, did it even have a chance of having symmetry? Notice if I add one more carbon onto the left-hand side here, like adding one more carbon right here, I wouldn't be worried about this having symmetry. The left-hand side is different than the right-hand side. There's no chance it could be Meso anymore. But again, let's take that off. And now I see, oh yes, it has a chance of being symmetrical. And same thing here. Yes, it has a chance of being symmetrical. And when it has that chance of being symmetrical, we can see another way to recognize that it's the Meso version. Look at your chiral centers here. And for Meso compounds that have 2 chiral centers, because it's going to be optically inactive, one of them has to be R and one of them have to be S. If they're both R or both S, those are chiral compounds. They will be optically active. And so in this case, even though I can't see if there's a mirror plane, I could figure it out by just simply assigning R and S. I can recognize it has a chance for symmetry, so now I'll assign R and S. In this case, 1, 2, 3. This guy's R, hydrogen's in the back. So 1, 2, 3. This guy looks like R, but the hydrogen's a wedge coming out, so it's really S. And this is indeed the Meso compound. It is achiral. It will not rotate light. Life is good. Cool. So for compounds that are not that are on a straight chain like this, for recognizing them as Meso, so as long as we're just talking about 2 chiral centers, one's going to have to be R, one's going to have to be S, again, for molecules with a chance of symmetry. Now, if you've got a molecule that is a ring, so let's say I gave you something like this, and I put this one here. So it turns out recognizing Meso compounds is going to be a common question you'll encounter on the exam for this chapter. And if you look at this lovely molecule here, there are chiral centers right here. So 2 chiral centers. However, you can also see that there's a lovely internal mirror plane, a sigma plane right down the middle of that molecule. And that makes it a Meso compound. And Meso compounds are much easier to recognize on cycloalkanes than they are on straight chains. Because for a cycloalkane, you can't rotate the carbon-carbon bonds in any kind of crazy way so that you can't see the mirror plane. For a cyclic compound like this, if there's a mirror plane, you're going to see it. But for one that's on a straight chain, you can rotate all those carbon-carbon bonds and put it in any kind of crazy conformation you want. And so maybe it's Meso, and here I can totally see it's Meso. 2 chiral centers, mirror plane, done. But I could put this in a conformation where we couldn't see that mirror plane. And it only has to have that mirror plane in one of the many conformations possible for it to be achiral. And so once again, so the rings are much easier, the straight chains though, so you might assign R and S as another way to figure out. Now notice you could do the same thing here, but I can see it. So, but if you assign R and S, you'll find out that one of these has to be R and one of these has to be S as well. And so in this case, this bromine's number 1, this carbon's number 2, this carbon's number 3, and this guy's in the R configuration. Bromine's number 1, this carbon's number 2, this carbon's number 3, and this one is in the S configuration. And lo and behold, that's going to be true for our Meso compounds. Again, as long as they have a chance for symmetry, and if you've got exactly 2 chiral centers, you go to assign R and S, life is good. Now, if you've got more than 2 chiral centers, and this is not something you will come across, you can't just say one's R and one's S because you've got more than 2. So, but again, that's not likely something you're encounter. You're going to see Meso compounds most often, and maybe even all the time, for what you see in an undergraduate organic chemistry class, in this kind of setting where you have exactly 2 chiral centers. Now, if you've benefited from this lesson, please consider giving me a like and a share. One of the best things you can do to support the channel. Or if you just simply feel sorry for short, bald guys, please consider giving me a like and a share. So if you're looking for the study guides that go with this lesson, or if you're looking for practice problems in dealing with isomers and stereochemistry, consider taking a look at my premium course on chadsprep.com.